This is a spin system in physics, and this is a deep neural network in machine learning. And guess what? They are equal twins. What I mean is, they are mathematically equivalent. And this equivalence can potentially revolutionize AI. To see what I mean, imagine your best friend has an equal twin that you have never met. How easy would it be for you to guess this unseen person's height? In the case of deep neural networks, its equivalence with the spin system in physics means we can immediately transfer centuries of knowledge to this new field. That is the type of revolution I will talk about today. But before I get into the main subject, let's first see what deep neural networks are in machine learning and what are spin systems in physics. Perhaps over the past 2 years you have been using ChatGPT, Google Gemini's, or other similar chat models. These are built based on what we call deep neural networks. The concept of neural networks dates back to the 1940s and 50s, inspired by biological neurons in our brains. Early pioneers like Warren McCulloch and Walter Pitts proposed a model of artificial neurons that could be connected to perform logical functions. But it wasn't until 1980s that neural networks gained practical applications with the introduction of backpropagation, a key algorithm for training networks with multiple layers. Today, deep neural networks power much of the technology we use daily, from recommendation systems to self-driving cars to generating artificial images to making artificial movies. At its core, a neural network is a mathematical structure designed to process data through layers of interconnected nodes, called neurons. Each neuron in a network holds a binary type value, like 0 and 1 or -1 and 1. The neurons in the first layer are the columns of our spreadsheet data. If our data is, for example, an image, the first layer could represent pixel values of that image. The input layer then feeds into one or more hidden layers. The very last layer is the output of the model that predicts what we trained the model for. Let me explain more with a simple example. Let's assume I have collected some data in the form of 28 times 28 pixel images. That means my images have a total of 784 pixels. Each pixel would be a neuron in the very first layer of my deep neural network. Let's now assume my goal is to predict handwritten digits. That means I give the model an image of a handwritten digit and it predicts the actual number. In this case, the last layer consists of 10 neurons, each neuron representing a digit from 0 to 9. The goal is for the neuron associated with the correct digit to activate. By activation, we mean take the numeric value of 1 rather than -1. For example, if my handwritten image shows the digit 0, the first neuron in the output layer must be 1 activated, and the rest of the neurons must take the value of -1, remain inactive. The connections between neurons have weights, which determine how strongly one influences the other. When an input goes through the network, it is processed through these weighted connections, allowing the network to detect features and patterns in the data. Before I move forward, let me introduce the consulting service that we offer at CompuFlair that can help your business with data-driven solutions. We can help if you need predictive analytics, risk assessment, downtime forecasting, pipeline automation, customer behavior insights, or any type of cutting-edge machine learning model. If interested, reach out to our website and fill out this form to start. Back to the video. Despite the remarkable success of deep neural networks in powering many of the technologies we use daily, these powerful models have some significant limitations that motivates researchers to seek improvements. First, understanding how a deep neural network arrives at its decisions remains a significant challenge. This problem is often referred to as the interpretability problem, and the deep neural network is often called a black box. Now imagine we prove the mathematical equivalence between a deep neural network, a black box, and a physics system that we know very well, a transparent box. Then all of a sudden, I know what is going on inside the black box by watching the transparent box. This is the concept of correspondence in physics, which I will discuss further in this video. Another problem of deep neural networks is that they require vast amount of data and computational resources to train. For example, the cost of training the GPT-4 model was more than $100 million. This is mostly due to the high number of parameters that we need to train to get these models to a functional stage. For example, a model like GPT-4 has around 1 trillion free parameters to be trained, and the existing algorithm for training these 1 trillion parameters is similar to a brute force approach. On the other hand, most areas of physics are heavily built on top of a branch of mathematics called group theory. Now, this group theory acts like a magic tool. It can all of a sudden tell us, hey, if GPT-4 has 1 trillion free parameters, I can already tell you the values for example, half of them. That means we don't need to spend money to train 500 billion parameters. If there was a linear relationship between the cost and the number of parameters we have to train, this means in the case of GPT-4, we could immediately save $50 million of the $100 million total cost. I will talk more about this group theory feature in terms of deep neural networks later in this video. For now, let's just accept that the challenges of deep neural networks can be significantly elevated if we find an equivalent physics system that we know very well. In physics, the technical word for such an equivalence between two widely different systems is correspondence. Okay, now it's time to get a bit deeper into the concept of correspondence in physics. In physics, correspondence serves as a bridge between different theories, showing how one theory reduces to another under specific conditions. To better imagine the correspondence, it is a bit like finding out that the rules for a game in 3 dimensions can somehow be explained by the rules of another all-time game that was played in just 2 dimensions. In physics, one of the most famous examples is the correspondence principle, introduced by a great physicist named Niels Bohr. This correspondence principle helped validate quantum mechanics by showing that it didn't completely replace classical mechanics, but rather extended it to account for atomic and subatomic phenomena. In physics, correspondence can reveal surprising connections between fields that might seem very different at first. A famous example is the ADS-CFT correspondence in string theory. This idea connects 2 types of theories, one that describes gravity in a special kind of higher dimensional space known as anti-de Sitter or ADS space, and another that describes particle interactions in a lower dimensional space, a conformal field theory or CFT. This connection is valuable because it lets physicists learn more about one theory by studying the other. For instance, understanding the theory of gravity can help with questions about particle interactions and vice versa. This surprising link has helped reveal new insights into both gravity and quantum theories. And this is the sort of equivalence that we are trying to establish between deep neural networks and the spin system in physics to help us solve the challenges of building and training deep neural networks. So far in this video, we have become familiar with deep neural networks and found out about their problems. We also discussed how an equivalent physics system can significantly improve the way we build and train deep neural networks. At this point, I need one more step before getting into building the equivalence between deep neural networks and a spin system in physics. And that step is to see what a spin and a system of spins are. To put it simply, a spin is an intrinsic form of angular momentum that particles like electrons possess. In classical physics, if you have a charged particle moving in a loop, it generates a magnetic field, behaving much like a tiny magnet. However, electrons, for example, act like magnets even when they are not looping around, something classical physics cannot explain. This magnetic behavior suggested a new type of angular momentum, so physicists introduced a spin as a fundamental property of particles. Electrons and most other elementary particles have only two possible spin orientations, which we call a spin up and represent by a numeric value of +1, and a spin down, which we represent by a numeric value of -1. This discreteness in values of the spin originates from its quantum nature. But to study the statistical behavior of a bunch of spins, we don't need to worry about the quantum stuff. So let's simplify a bit. Let's represent a spin by an arrow that can only be upside up or upside down, and no other configuration like 45-degree rotation is allowed. Now, we can already see how similar the two states of our spin and a neuron in a deep neural network are. Both of them have only two possible states. Active or spin up is represented by the number +1, and inactive or spin down is represented by the number -1. Now that we have established what a spin is, let's look at how these spins interact with each other in a system. One of the simplest models that describes a system of interacting spins is called the Ising model. Imagine a grid of spins, where each spin can point either up, represented by +1, or down, represented by -1. In the Ising model, the total energy of this system depends on the orientation of these spins, their interactions, and the external magnetic field that might be present around these spins, and has two main parts. The first part of the energy is influenced by an external magnetic field, which we represent by symbol B. When B is positive, it pushes the spins to point up because it lowers the energy of the system. It kind of applies a magnetic force to each of the individual spins. The second part of the energy of the system of spins describes interactions between neighboring spins. The interaction energy between a spin is represented by the symbol J. If J is positive, the spins want to align in the same direction, either both up or both down. This is called a ferromagnet. If J is negative, the spins want to be in opposite directions, one up and one down, which is called an anti-ferromagnet. Before I go deeper into this system and discuss the different conditions in which different forces win the competition and how the overall system will look under each condition, let me first establish the equivalence of this system of spins and a deep neural network with the following design. I will mathematically prove these equivalences in the next chapter of the video, but for now, just accept that the hidden neurons and the output neuron are the spins in the Ising model, and I represent all of them with a vector S. Each component of the vector S refers to the numeric value +1 or -1 that the corresponding spin or the neuron takes. Now, the index of vector S refers to its corresponding component. That means S with index 1 or just S1 refers to the first spin or neuron. S with index 2 or S2 refers to the second spin or neuron, etc. The edges between hidden neurons and the output neuron in the deep neural network correspond to the interaction term J in the spin system. The neurons in the first layer of the deep neural network, the input neurons, together with the edges between the first and second layer, correspond to the external magnetic field in the spin system. Okay, now that we have established the correspondence between different objects in the deep neural network and the spin system, let me walk you through the type of information we can immediately transfer from the Ising model to deep neural networks. Most textbooks in statistical physics have a fairly good description of the Ising model. So let's, for example, use this book to walk through the literature of the Ising model, and as I scroll down the pages, I will explain what each part means in terms of deep neural network given its correspondence with the Ising model that we just discussed. This equation is just the total energy of the system. The sum is over the spins, which in terms of a deep neural network is the sum over all the neurons except the ones in the input layer. And I will mathematically establish these sums in the next chapter. If we scroll down, we come across this equation, which is the probability description of the spin system. This is already in the form that I refer to as the God equation in this series of YouTube videos. If you wonder why I call it the God equation, watch the first video in the playlist. Scrolling down the pages, the book describes the creation of a new variable called magnetization defined by this equation. In machine learning, this process of defining new variables is called feature engineering. This figure shows different landscapes of the probability in terms of spins, or neurons in the deep neural networks. As you can see, there is a critical temperature. If our system's temperature is above that, the landscape will look like the left figure. If our system's temperature is below temperature, the landscape will look like the right-hand side figure. In terms of a deep neural network, the temperature is tuned by the input layer of the neurons in the first layer of the network. And here are how spins, all the neurons except the ones in the first layer, will look like under different conditions. In these figures, the colors represent the up or down state of spins. In terms of deep neural networks, the color shows the activation state of neurons or inactivation of them. Each pixel of this image is a neuron. Yellow means that neurons are active and blue means that neurons are inactive. Again, the temperature is tuned by the input neurons in a deep neural network. At high temperatures, the neurons are randomly active or inactive. As we decrease the temperature, the neurons tend to clump together, and neighbor neurons tend to behave similarly. Either all be active or all be inactive. When the temperature goes below the critical temperature, neurons tend to be more active and we still see the clumping behavior. And a mysterious behavior happens when the temperature is equal to the critical temperature. In this case, if we zoom out, the picture will not change. In terms of deep neural networks, it means the behavior of the model will not change no matter how many more layers of hidden neurons we add to the model. Before I move forward, let me just mention that how to systematically mine these insights and transfer them to our existing technologies like GPT models, for example, takes a dedicated research community. Also, if we scroll further down the pages of this book, we see a concept is mentioned very often: symmetry. This is so fundamental in physics that I cannot emphasize enough. And given the correspondence that I just presented, it can be fundamental and revolutionary in deep neural networks as well. Before discussing symmetries, I better first get into the mathematics and prove the correspondence between the Ising model of spins in physics and deep neural networks in machine learning. Only after that I can get deeper into symmetries and speak about how they can help. Let me first draw the roadmap of what I'm going to do and then get down and do it. So on the one hand, we have a deep neural network, and on the other hand, I have a spins system. Both of the systems are made of a bunch of mathematical variables that take the same two states of plus and minus 1. That means when we write the math for each of the two systems, the math doesn't ask us if this variable S represents a spin or if it represents a neuron. It's just the same variable describing a neuron and a spin. To establish the equivalence of the two systems, what I need to show is that the same probability function, let me emphasize, the same probability distribution governs the behavior of the vector S in the two systems, the deep neural network and the spin system. In other words, if only the mathematical form of their probabilities is given to us, we cannot tell from the math if we are talking about the deep neural network or if we are talking about the system of spins, because one mathematics is describing the two systems. Okay, now let's down to the details. In physics, the behavior of the spin system is described by this probability equation, where E is the system's total energy that we discussed earlier in the video. It is made of these two terms that are themselves in terms of the components of the spin S. So the probability of the spin system is already in the form that we want it to be, the God equation format. Let's now derive the probability of the neurons in the deep neural network and show that it is the same as in the spin system. I'm going to start with one single neuron, derive its probability description, and then add the rest of the neurons. And to proceed, I need to ask a question. What does it take for a neuron to become active and take the value of +1? And what does it take for the neuron to remain inactive and take the value of -1? Let me first explain the general concept, which is actually taken from biological neurons. In this video, which is in the same playlist as our video today, I have explained how the actual neurons in the brain work. A neuron in the brain receives electric voltages from neighbor neurons. These electric voltages are in the form of excitatory or inhibitory. That means they can also cancel each other. But when the total sum of the voltages, positive and negative, is above a threshold, the neuron fires. In other words, it becomes active. The same concept is used to build an artificial neuron. If the sum of the inputs from the rest of the neurons, which can be positive and negative, is above a threshold, that neuron becomes active. In other words, it takes a value of +1. Otherwise, it remains inactive and takes a value of -1. The activation function that takes these two values of +1 and -1, given the amount of input that the neuron receives, is hyperbolic tangent, or simply tan H. Let me just mention that there are other types of activation functions that we could use for neurons, and conceptually they are not much different. The sigmoid function is another example. In this video, another one in this series, I discussed the probability distribution that leads to the sigmoid function. Okay, now that we discussed how neurons become active or remain inactive, let's get back to the single neuron system and find the probability distribution that leads to the tan H activation function for the neuron. And I already know the form of the probability function using physics concepts. And here it is. If you are interested in seeing how I guessed this probability form, watch this video. But we don't need an interpretation of this probability to show that it leads to tan H activation, because I'm going to derive it now. We know that sum of all the probability states must be 1. Therefore, Z, which we call partition function in physics, must be equal to this term. Now, I multiply by 1. That means I multiply the partition function by this exponential term and then set j equal to 0 at the end of any calculation. By a simple derivative, I can find out that the expected value of the neuron state S is just the following derivative of the partition function with respect to j. And remember, I have to set j equal to 0 at the end. Let's first calculate the partition function and then take the derivative. For that, I just need to expand the sum explicitly. And here's the partition function. Now, if I take a derivative of it, divide it by itself, and then set j equal to 0, I know it would be the expected value of the neuron, which looks like this. And this is just the tanh function. There is just one parameter that I intentionally haven't discussed it. How to fix the beta in the probability function. Remember that we want our tanh to be the activation function that people are already using in deep neural networks. So I just need to compare my equation with the practical activation function. That comparison sets the beta to be the following sum. From the literature on deep neural networks, I know that W0 is the bias and rest of the values are the weights, and X variables are the inputs from the neurons in the first layer or the previous layer. Okay, I have the probability distribution that describes the activation of a single neuron. I can now use it to construct the probability distribution of deep neural networks. For simplicity, let's work with this neural network design with only one hidden layer. The procedure will be the same if I add more hidden layers. It just makes the math longer. If the states of the neurons in the hidden layer are given, the probability of the activation state of the output neuron is what we just derived in the case of a single neuron. Since each hidden neuron itself has a probability for its two activation states, the total probability of the system is just the multiplication of the output neuron's conditional probability times the probabilities of each of the hidden neurons. We know that the multiplication of a bunch of exponentials is equal to the exponential of the sum of their arguments. So the total probability distribution would be the following. I have color-coded the terms so that we can easily find out where they are coming from. Note that in this probability distribution, the X values come from the input layer and are therefore fixed by the dataset. Also, the W variables are supposed to be determined through training. The conventional training method is the backpropagation. In this video, I discussed an alternative training method that I guess is more efficient if we spend the time to systematically develop it. But no matter how we train the model, W's are also fixed. Therefore, the probability distribution is only a function of the neuron state's S variables. Also notice that some of the terms contain only a single neuron state S, and some other terms contain two neuron states multiplied. Let me now introduce a vector B whose components are defined to be equal to the coefficients of single spin terms in the sum. I also introduce a matrix J whose components are defined to be equal to the coefficients of the double spin terms in the sum. Now I can rewrite the probability in the following form. And if I compare it to the probability distribution in the spin system in physics, they are mathematically the same, with B being the magnetic field and J being the interaction. If we look closely, we see that B and J in the probability distribution of deep neural networks have indices. But in the version of the Ising model that we discussed earlier in the video, all the components of B and J were the same. And for that reason, we had taken them all out of the sum. But that was just a toy model that the book had started with. If we scroll down the pages of that same book, it mentions that we have to take the spatial dependence of terms into account to be more realistic. Now, why do I and J indices refer to spatial positions of spins? It's because each spin in the Ising model is located at a different position in a space, and the indices I and J are actually enumerating the spatial sites of the spins. Simply speaking, deep neural networks do not correspond with the toy version of the Ising model, but instead correspond with the field theory version of it. That means taking the spatial dependence into account, the probability of the Ising model of the system of spins will exactly be the same as the probability of the deep neural network such that from the mathematics alone, we cannot tell which system the math is referring to. That means the two systems behave exactly the same. Knowing the one that is considered a transparent box will mean we know everything about the other that is considered a black box. Therefore, this equivalence can actually solve the black box problem of deep neural networks. Now, let me briefly discuss how symmetry can reduce the computation needed for training the model. First, remember that the J matrix and B vector are defined in terms of the weights and biases in the deep neural network. That means when we talk about training the model, we mean we want to estimate the values of the J matrix and B vector. Okay, now a probability function has a type of symmetry. It will reflect itself as an invariance in various moments of the expectation values of the dataset, such as the averages, covariance matrices, etc. For example, let's say I use a simple Python code to compute the averages of the output neuron in the dataset. Then I multiply the output neuron's state by a -1 in the entire dataset and then recompute the average of the output neuron. If the two averages turn out to be the same, then the corresponding component of the B vector must be 0. To see the reason, we can explicitly write the equation for the average of the output neuron and then flip the sign of that neuron mathematically everywhere in the equation. Another usage of symmetries is in the classification of the designs of deep neural networks. In this case, I will first write down my required behavior from the neural network and then see which symmetry group adheres to that requirement, and then impose that symmetry in terms of certain constraints on the B and J matrix. The constraints will then reduce the number of independent components in these objects, which in turn eliminates the need for estimating them. Also, the probabilistic version of deep neural networks can help us reduce the computations by allowing us to train the model by computing the empirical average, covariance matrix, and higher moments of expectation values of the columns in our spreadsheet, and solve the resulting system of equations to estimate the values of the unknown parameters. Unlike the conventional approaches, this method does not try to minimize a loss function. Hence, it does not suffer from the known problems of minimization in high dimensions. I have explained this approach in more detail in this YouTube video and recommend you to watch that as well. Before I end this video, let me introduce a high-ticket bootcamp program that we offer in CompuFlair. If you're looking to break into data science, I have created a unique high-ticket bootcamp that might be for you. This program isn't just a bunch of courses. It's about transforming you from where you are now to the hero stage that companies will love to hire. The key features of this program are: first, it will be completely customized to your conditions. Second, you will have daily access to me through Zoom calls, direct messages, and email. And I'll be there to guide you closely every step of the way. And if you don't know me, I have a PhD and a master's degree. Have been a data science fellow of the National Library of Medicine, have gone through postdoctoral training programs, and I'm the founder of CompuFlair LLC, registered in Texas, mainly offering data science consulting services. In this high-ticket bootcamp program, you will learn the tools of data science, and together with me, we'll build your online portfolio and presence, and prepare for job interviews. We also ensure that you develop the skills and insight that AI cannot replace, so that your role stays essential. Now, since I'm just one person and want to dedicate whatever time this zero to hero transition takes, I can only accept a few people at a time. But if you apply and are qualified, you will be queued for the next available spot. And the only prerequisite for this program is a college-level understanding of mathematics. If interested, go to the link in the description below and fill out the application form. If we look like a good match, we'll schedule a quick chat and move forward from there. I hope you enjoyed this video. Take care, and I'll see you in the next video.